Dear students, welcome back to physics class. Today, I would like to introduce the new topic elementary concepts of differentiation and integration for describing motion, part A. The subtopics are A. Obtain equations of motion for constant acceleration using method of integration, and B. Numerical part B. For today class, at first I am going to discuss on how to obtain equations of motion for constant acceleration using method of calculus or integration method. First I am going to derive the equation V is equal to V0 plus AT, which is the first kinematic equation using method of calculus. We know that rate of change of velocity gives acceleration, whose calculation by the usage of differentiation method was studied in last class. So, A is equal to dv by dt, which gives A dt is equal to dv, which is the equation A. Now we have to use the integration method. Before doing this, you have to notice this point. Integration is the reverse process of differentiation, which is represented by the symbol as shown in the given slide. Consider the variable y, which is a function of the variable x. Then it can be written as y is equal to fx. Suppose this function gives this equation y is equal to x the power of n. You know that when y is differentiating with respect to x, it gives dy by dx. That is rate of change of y with respect to x, whose result will be dy by dx is equal to n x the power of n minus 1 dx by dx. Since dx by dx is equal to 1, it will be equal to dy by dx is equal to n x the power of n minus 1. It is considered as general form of result by the differentiation. For example, y is equal to x the power of 5. Then what should be dy by dx, which will be equal to 5x the power of 4 dx by dx is equal to 5x the power of 4. But for integration method, which means that the summation of all infinitesimal values, that is, it is just opposite process of differentiation. As y is equal to fx, that is, y is the function of x, then when it is applied the integration calculus method, it will form as integration of y dx is equal to integration of fx dx. Suppose we have considered the previous result of the y is equal to fx as x the power of n, whose integration gives this result, which is the form of integration of y dx is equal to integration of x the power of n dx is equal to x the power of n plus 1 divided by n plus 1 plus c, where c be the integration constant. For example, y is equal to x the power of 5, then integration of x the power of 5 dx is equal to x the power of 5 plus 1 whole divided by 5 plus 1 is equal to x the power of 6 by 6 plus c. This mathematical calculus method is applied to solve our physics problem. From equation A, a into dt is equal to dv. By integrating the expression, we get integration of a dt is equal to integration of dv. More precisely saying, it can be written as 0 to t integration of a dt is equal to v0 to v integration of dv, where t is equal to 0 and t is equal to t be the initial and final values of time, or they are lower and upper limit values of time t by integration. Similarly, v0 and v be the initial and final values of velocity or lower and upper limit values of velocity v by the integration. Then 0 to t integration of a dt is equal to v0 to v integration of dv. As a, which is uniform acceleration, is constant, it must be taken out of the integration symbol. So it will become as a into 0 to t integration of dt is equal to v0 to v integration of dv. Here, by applying limit, we have to take the difference of upper and lower limited values of the same quantity. So, it will be taking in the form of a into t minus 0 is equal to v minus v0, then v minus v0 is equal to at. So, v is equal to v0 plus at. Hence, we have derived the first kinematic equation by the method of integration. Now, I am going to derive second kinematic equation, which is x is equal to v0 t plus 1 by 2 at square using the method of integration. We know that v is equal to dx by dt. Rate of change of displacement gives velocity, which is instantaneous velocity. Then v into dt is equal to dx. When integration method is applied on this expression, we get 0 to t integration of v dt is equal to x0 to x integration of dx, where 0 and t be the lower and upper limits of the time t and x0 and x be the lower and upper limits of the position x by this integration. Since v is equal to v0 plus at, the expression becomes as 0 to t integration of v0 plus at dt is equal to x0 to x integration of dx, which gives 0 to t integration of v0 dt plus 0 to t integration of at dt is equal to x0 to x integration of dx, which is the equation b. Here we have to consider the LHS of the expression, which is 0 to t integration of v0 dt plus 0 to t integration of at dt, which is equal to v0 into 0 to t integration of dt plus a into 0 to t integration of t dt, where v0 and a be the constant, so we should take this constant out of the integration symbol. Then v0 into 0 to t integration of dt plus a into 0 to t integration of t dt, which is equal to v0 into t minus 0 plus a into t square by 2, the lower limit 0 and upper limit t. You have to remember that integration of x the power of n dx is equal to x the power of n plus 1 whole divided by n plus 1. Here, by ignoring the integration constant. So, LHS of the expression becomes as v0t plus a into t square by 2 is equal to v0t plus 1 by 2 at square. Now we have to consider the RHS of the expression, which is x0 to x integration of dx, which gives x, the lower limit is x0, the upper limit is x is equal to x minus x0. This expression b becomes as v0t plus 1 by 2 at square is equal to x minus x0. So, x minus x0 is equal to v0t plus 1 by 2 at square, then x is equal to x0 plus v0t plus 1 by 2 at square. When initial position x0 of the uniformly accelerated body is considered as 0, the expression x is equal to x0 plus v0t plus 1 by 2 at square becomes as x is equal to v0t plus 1 by 2 at square. That is, x0 is equal to 0. Hence, we derived the required expression. Now, I am going to derive the third kinematic equation v square is equal to v0 square plus 2ax by using the same method. We know that a is equal to dv by dt, which means that rate of change of velocity gives instantaneous acceleration, which can be written as dv by dt is equal to dv by dx into dx by dt. It is the same result by the cancellation of 2 dx in the equation. So, a is equal to dv by dx into dx by dt is equal to dv by dx into v. Since v is equal to dx by dt, which is the rate of change of displacement, that is, a is equal to v into dv by dx. Then a into dx is equal to v dv, which is the expression c. When we apply the integration method on the expression c, we get x0 to x integration of a dx is equal to v0 to v integration of v dv, which gives a into x0 to x integration of dx is equal to v0 to v integration of v dv. So, the equation will become as a into x minus x0 is equal to v square by 2. The lower limit is v0 and the upper limit is v. Since integration of x the power of n is equal to x the power of n plus 1 divided by n plus 1, which is equal to v square by 2 minus v0 square by 2 is equal to 1 by 2 into v square minus v0 square. So, a into x minus x0 is equal to 1 by 2 into v square minus v0 square. Then 2a into x minus x0 is equal to v square minus v0 square. So, v square is equal to v0 square plus 2a into x minus x0. As initial position x0 is equal to 0, the expression will become as v square is equal to v0 square plus 2ax. Hence, we have derived the required expression. On next, let us discuss on numerical. First question is, two trains A and B of length 400 meter each are moving on two parallel tracks with a uniform speed of 72 km per hour in the same direction. With A ahead of B, the driver of B decides to overtake A and accelerates by 1 meter per second square. If after 50 seconds the guard of B just brushes past the driver of A, what was the original distance between them? What is its solution? Given that initial velocity of the train V0 is equal to 72 km per hour, which is equal to 20 meter per second. Here we have converted kilometer per hour into corresponding value in meter per second, since 1 kilometer per hour is equal to 5 by 18 meter per second. Time t is equal to 50 seconds and acceleration a is equal to 0 meter per second square, since it is moving with a uniform velocity. There is no change in velocity per unit time, so acceleration a is equal to 0. We have to find the distance x traveled by the train A. We know that second equation of motion gives the distance x covered. X is equal to V0t plus 1 by 2 at square. By substituting the values of V0, A and t, we get 20 meter per second into 50 seconds plus 1 by 2 into 0 into 50 second all square, which is equal to 1000 meter is equal to 1 kilometer. Now we have to consider the train B, given that initial velocity V0 dash is equal to 72 km per hour, which is equal to 20 meter per second. Acceleration A dash is equal to 1 meter per second square and time t is equal to 50 seconds. Why should be is acceleration 1 meter per second square? Because the driver of the train B decides to overtake the train A, which is achieved by this acceleration. We have to apply the second equation of motion to find the distance x dash covered by the train B. So, x dash is equal to V0 dash t plus 1 by 2 a dash t square, which is equal to 20 meter per second into 50 second plus 1 by 2 into 1 into 50 seconds all square, which is equal to 2250 meter. So the original distance between the driver of train A and the guard of train B is equal to 2250 minus 1000 is equal to 1250 meter. And second question is, a player throws a ball upwards with an initial speed of 29.4 meter per second. A. What is the direction of acceleration during the upward motion of the ball? B. What are the velocity and acceleration of the ball at the highest point of its motion? C. Choose the x is equal to 0 meter and t is equal to 0 second to be the location and time of the ball at its highest point. Vertically downward direction to be the positive direction of x-axis, and give the signs of position, velocity and acceleration of the ball during its upward and downward motion. And D. to what height does the ball rise and after how long does the ball return to the player's hand. Take g is equal to 9.8 meter per second square and neglect air resistance. For solving this question, you have to understand some points which are acceleration of the ball, which is actually acceleration due to gravity, always acts in the downward direction towards the center of the earth, which is irrespective of the direction of its motion. At maximum height, velocity of the ball becomes to be zero. Acceleration due to gravity at a given place is constant and acts on the ball at all points, including the highest point, with constant value, that is 9.8 meter per second square. So, the sign of position is positive, sign of velocity is negative because of it has decreased in upward motion, and sign of acceleration is positive during the upward motion. During downward motion, the signs of position, velocity and acceleration all are positive. You have to remember that the direction of acceleration during the upward motion of the ball is downward. Here, velocity, which is the final velocity, which is equal to 0. Acceleration is equal to 9.8 meter per second square and x is greater than 0 for both upward and downward motions. But v is less than 0 for upward motion and v is greater than 0 for downward motion, and a is always greater than 0 throughout the motion. But in upward motion, acceleration due to the gravity is negative, which is minus g is equal to minus 9.8 meter per second square. Given that initial velocity of the ball v0 is equal to 29.4 meter per second, its final velocity v is equal to 0. At maximum height, the velocity of the ball becomes to 0. And acceleration a is equal to minus g, which is equal to minus 9.8 meter per second square. Here we have to apply the third equation of motion to find the height x of the ball reached, which is the distance traveled by the ball in upward journey. Then v square is equal to v0 square plus 2ax. Here a is to be replaced by minus g. Then x is equal to v square minus v0 square whole divided by 2a, which is equal to v square minus v0 square whole divided by 2 into minus g. On substituting these values of v, v0 and g, we will get x is equal to 44.1 meter. We have to use the first equation of motion to find the time of action t, since the total time taken by the ball to return to the player's hand is 2 into time of action, or time of action plus time of descent, which is the time of flight. What is time of action? It is the time taken by thrown up body to reach to maximum height. And what is time of descent? It is the time taken by a freely falling body to reach on the ground. Here, the total time taken by the ball to return to the player's hand is equal to time of action plus time of descent, because time of descent is equal to time of ascent. This total time is equal to time of flight. We know that time of ascent t is equal to v minus v0 whole divided by a, since v is equal to v0 plus at. So t is equal to v minus v0 whole divided by a is equal to v minus v0 whole divided by minus g. By substituting the values of v, v0 and g, we get time of ascent t is equal to 3 seconds. Then the total time taken by the ball to return to the player's hand is equal to 2 into time of ascent is equal to 2 into 3 seconds is equal to 6 seconds. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.